Welcome to Cosmic Whispers, where cosmic mysteries come alive. Your journey beyond the stars begins now. In the twilight hours of 1899, a brilliant mind stood atop Pikes Peak in Colorado Springs, watching nature's most spectacular electrical display dance across the Rocky Mountain sky. Nikola Tesla, the Serbian-American inventor, whose alternating current system would power the modern world, gazed at lightning bolts stretching across dozens of miles and conceived an audacious dream. What if humanity could harness this raw power and transmit it wirelessly across the entire planet? Tesla's vision wasn't mere fantasy. He understood that Earth itself was a massive electrical conductor, surrounded by an ionosphere crackling with electromagnetic energy. Lightning strikes our planet approximately 100 times every second, delivering roughly 1 billion volts and 30,000 amperes per bolt. Each strike contains enough energy to power an average American home for several days, yet this immense power dissipates in microseconds, lost to the atmosphere. The inventor's Colorado Springs laboratory became a testing ground for wireless power transmission. His massive coil system, standing over 50 feet tall, could generate artificial lightning bolts stretching nearly 130 feet through the air. Tesla demonstrated that electrical energy could indeed travel through the ground and atmosphere without wires, lighting bulbs and powering motors from considerable distances. But Tesla envisioned something far grander than laboratory demonstrations. He imagined a global wireless power system that could transmit electricity anywhere on Earth using the planet's natural electrical properties. His proposed Wardenclyffe Tower on Long Island was designed to tap into what he called the terrestrial stationary waves, standing electromagnetic patterns that could theoretically carry power around the globe. Every great journey starts with a few brave explorers. Right now, Cosmic Whispers is just beginning, and your support means everything. If you enjoy unraveling the mysteries of the universe, hit subscribe. It's free, and it helps us grow this community together. To understand Tesla's dream, we must grasp the staggering scale of Earth's electrical appetite today. Humanity consumes approximately 28,000 terawatt-hours of electricity annually. That's 28 trillion kilowatt-hours. If we could somehow capture and distribute just 1% of the lightning strikes occurring globally each year, we would need to harness roughly 365 million lightning bolts efficiently. The physics behind Tesla's wireless transmission concept relies on the Schumann resonances, extremely low-frequency electromagnetic waves that propagate in the cavity between Earth's surface and the ionosphere. These resonances, first predicted by physicist Winfried Otto Schumann in 1952, occur at frequencies around 7.83 Hz and several harmonics. Tesla intuitively understood that these standing wave patterns could serve as a global wireless transmission medium. Lightning itself represents one of nature's most efficient energy transfer mechanisms. During a typical thunderstorm, electric charges build up in clouds through collision processes involving ice, particles and water droplets. When the electric field strength reaches approximately 3 million volts per meter, the air becomes ionized, creating a conductive channel through which massive electrical currents can flow. The stepped leader, a faint branching channel of ionized particles, descends from a cloud toward the ground in a zigzag pattern. When it approaches within 100 to 200 meters of the surface, upward streamers rise from elevated objects. The moment these channels connect, a powerful return stroke surges upward at approximately 1/3 the speed of light, creating the brilliant flash we perceive as lightning. Tesla's genius lay in recognizing that this natural process could potentially be controlled and directed. His wireless power transmission experiments suggested that artificial lightning could follow predetermined paths through the atmosphere and ground, delivering electrical energy precisely where needed. The question that haunted him, and continues to fascinate scientists today, remains tantalizingly simple yet profoundly complex. Could we actually illuminate our entire planet using controlled lightning? The electromagnetic foundations underlying Tesla's wireless power transmission dream rest upon principles that govern how electrical energy propagates through Earth's natural systems. Our planet functions as a massive spherical capacitor, with the conductive surface serving as one electrode and the ionosphere located approximately 60 to 1,000 kilometers above, acting as the opposing electrode. Between these layers exists what scientists call the Earth ionosphere waveguide, a natural transmission medium that carries electromagnetic waves around the globe. This planetary electrical circuit continuously processes tremendous amounts of energy. The ionosphere maintains a constant electric field of approximately 100 to 150 volts per meter near Earth's surface under fair weather conditions. This field results from thunderstorm activity worldwide, which acts like a global generator, pumping roughly 1,000 to 2,000 amperes of current through the atmosphere continuously. The Schumann resonances represent the key to understanding how electromagnetic energy can propagate globally. These resonances occur because electromagnetic waves can establish standing wave patterns between Earth's surface and the ionosphere. The fundamental Schumann resonance frequency of 7.83 Hz corresponds to electromagnetic waves that travel around Earth's circumference approximately 7.5 times per second. To visualize this phenomenon, imagine Earth as a massive resonating cavity. Just as a musical instrument produces specific frequencies based on its physical dimensions, our planet supports particular electromagnetic frequencies determined by its circumference and the height of the ionosphere. These standing wave patterns create nodes and antinodes, regions of minimum and maximum electromagnetic field strength, distributed across Earth's surface. Tesla's wireless power system would theoretically exploit these natural resonances by injecting electromagnetic energy at precise frequencies and phases. His transmitter would act like a giant antenna, exciting the Earth ionosphere cavity at its resonant frequencies. The energy would then propagate as standing waves, potentially accessible anywhere on the planet through properly tuned receiving equipment. However, the physics of global wireless power transmission presents formidable challenges. Electromagnetic waves propagating through the Earth ionosphere waveguide experience significant attenuation, energy loss as they travel. The conductivity of both Earth's surface and the ionosphere varies dramatically with location, time of day, season, and solar activity, creating unpredictable propagation conditions. The ionosphere itself undergoes constant changes due to solar radiation. During daylight hours, increased solar ultraviolet radiation creates higher electron densities in the ionospheric layers, altering their electrical properties. Solar storms can dramatically disrupt ionospheric conditions, potentially rendering wireless power transmission unreliable or impossible during space weather events. Ground conductivity presents another significant variable. Seawater, with its high salt content, conducts electricity far better than dry soil or solid rock. Tesla's system would encounter vastly different propagation characteristics when transmitting across oceans versus continents, mountainous regions versus plains, or areas with different geological compositions. The inverse square law governing electromagnetic radiation poses perhaps the most fundamental challenge. As electromagnetic waves propagate outward from a point source, their intensity decreases proportionally to the square of the distance traveled. Even if Tesla's transmitter could efficiently couple energy into the Earth ionosphere waveguide, the power available at distant locations would be dramatically reduced. Atmospheric absorption further complicates global wireless transmission. Water, vapor, oxygen, and other atmospheric constituents absorb electromagnetic energy at specific frequencies. While the Schumann resonance frequencies experience relatively low atmospheric absorption, the power levels required for practical wireless transmission would need to overcome these losses. Tesla's proposed solution involved creating what he termed terrestrial stationary waves, standing wave patterns that could theoretically maintain their amplitude across vast distances. He believed that by precisely matching his transmitter's frequency and phase to Earth's natural electrical resonances, he could establish efficient energy transfer pathways that would circumvent traditional radiation losses. Modern analysis suggests that while Tesla's theoretical framework contained elements of valid electromagnetic theory, the practical implementation of global wireless power transmission faces insurmountable efficiency challenges. The energy losses inherent in electromagnetic propagation through the Earth ionosphere system would require transmitter power levels far exceeding any practical generating capacity. Understanding lightning as a potential power source requires examining the extraordinary energy concentrations occurring within these brief but powerful electrical discharges. A typical lightning bolt carries approximately 5 billion joules of energy, though only about 1 to 5 billion joules reach the ground during a cloud-to-ground strike. This energy concentration represents one of nature's most intense electrical phenomena, with peak currents reaching 30,000 amperes and temperatures exceeding 30,000 degrees Celsius, hotter than the sun's surface. Lightning occurs through a complex charge separation process within thunderclouds. As ice particles and water droplets collide within the turbulent cloud environment, they transfer electrical charges through a mechanism known as triboelectric charging. Smaller particles typically acquire positive charges and are carried upward by air currents, while larger particles become negatively charged and settle toward the cloud's base. This process creates enormous electric fields, sometimes exceeding 1 million volts per meter within the cloud structure. The global lightning activity presents a staggering energy resource. At least in theory, Earth experiences approximately 8 million lightning strikes daily, concentrated primarily in tropical and subtropical regions. The Congo Basin in Africa generates the highest lightning flash rates globally, with some areas experiencing more than 70 flashes per square kilometer annually. The Amazon Basin, Southeast Asia, and parts of North America also contribute significantly to global lightning activity. Seasonal and diurnal patterns govern lightning distribution. Most lightning occurs during late afternoon and early evening, hours when atmospheric instability peaks due to solar heating. Summer months in each hemisphere produce the highest lightning frequencies, while winter periods show dramatically reduced activity. This temporal variation would create significant challenges for any lightning-based power system, as energy availability would fluctuate unpredictably with weather patterns and seasonal cycles. Theoretical lightning capture methods have been proposed by various researchers, though none have achieved practical implementation. The most straightforward approach involves tall conducting structures designed to attract and channel lightning strikes. However, lightning's unpredictable nature makes it impossible to guarantee when or where strikes will occur. Even the tallest structures, such as the CN Tower in Toronto, which experiences approximately 75 lightning strikes annually, cannot reliably predict strike occurrence. Benjamin Franklin's famous lightning rod experiments in the 1750s demonstrated that pointed conductors could attract electrical discharges, but these devices primarily provide protection rather than energy capture. Modern lightning protection systems are designed to safely conduct lightning currents to ground, dissipating the energy harmlessly rather than storing it for later use. The energy storage challenge represents perhaps the most significant obstacle to lightning-based power generation. Lightning delivers its energy in microseconds, creating power levels that exceed any known storage technology's absorption capacity. A typical lightning strike might deliver its 5 billion joules in approximately 200 microseconds, representing an instantaneous power level of 25 terawatts, roughly 1,000 times greater than the generating capacity of the world's largest power plants. Conventional battery technologies cannot absorb energy at such extreme rates. Even the most advanced supercapacitors, designed for rapid charging and discharging, cannot handle the power densities associated with lightning strikes. The electrical energy would need to be captured and converted to a form suitable for storage within the brief duration of the lightning discharge itself. Additionally, lightning's high voltage and current characteristics would require sophisticated power conditioning equipment to convert the raw electrical energy into forms suitable for transmission and storage. This equipment would need to respond within microseconds and handle extreme electrical stresses that would likely destroy conventional electrical components. Geographic distribution of lightning activity creates another fundamental challenge. While tropical regions generate abundant lightning, they often lack the electrical infrastructure necessary to distribute captured energy to population centers. Conversely, major energy-consuming regions in temperate climates experience relatively low lightning activity, creating a severe mismatch between energy availability and demand. the efficiency of lightning energy extraction remains highly questionable. Even if capture and storage technologies could be developed, the sporadic nature of lightning strikes would require massive overcapacity to provide reliable power generation. The infrastructure costs associated with lightning capture systems would likely exceed those of conventional power generation by orders of magnitude, making lightning-based power economically impractical regardless of technical feasibility. Contemporary wireless power transmission technologies have evolved far beyond Tesla's early experiments, yet they remain fundamentally limited by the same physical principles that constrained his 19th-century vision. Modern systems employ three primary mechanisms for wireless energy transfer: electromagnetic induction, magnetic resonance coupling, and microwave power transmission. Each approach offers distinct advantages and faces specific limitations when scaled to planetary applications. Electromagnetic induction, the principle underlying modern wireless charging pads for smartphones and electric vehicles, operates through alternating magnetic fields that induce currents in nearby receiving coils. This technology works efficiently over distances measured in millimeters to centimeters, but experiences rapidly diminishing efficiency as separation increases. The coupling coefficient between transmitting and receiving coils decreases exponentially with distance, making long-range power transmission impractical through inductive methods. Magnetic resonance coupling, pioneered by researchers at the Massachusetts Institute of Technology in the early 2000s, extends wireless power transmission range to several meters by matching the resonant frequencies of transmitting and receiving circuits. This technique achieved approximately 40% efficiency over distances of 2 meters in laboratory demonstrations. However, the power transfer efficiency still decreases significantly with distance, and the resonant frequency matching requires precise tuning that becomes increasingly difficult as environmental conditions change. Microwave power transmission represents the most promising technology for long-distance wireless energy transfer. This approach converts electrical energy into high-frequency microwave radiation, typically at frequencies of 2.45 GHz or 5.8 GHz, then transmits it through space using focused antenna arrays. The receiving end employs specialized antennas called rectifying antennas that convert microwave energy back into direct current electricity. The Japanese space agency, JAXA, has conducted extensive research into microwave power transmission for space-based solar power systems. Their experiments have demonstrated successful power transmission over distances exceeding 50 kilometers, achieving efficiencies approaching 80% under optimal conditions. These achievements represent the closest realization of Tesla's wireless power transmission dreams using modern technology. Satellite-based solar power concepts envision massive solar arrays positioned in geostationary orbit, where they would collect solar energy continuously without atmospheric interference or day-night cycles. These space-based power systems would transmit energy to Earth using focused microwave beams directed at receiving stations on the planet's surface. The receiving antennas would cover areas measured in square kilometers, converting the microwave energy into electricity for distribution through conventional power grids. The physics governing microwave power transmission align closely with Tesla's theoretical framework while addressing many of his practical limitations. Microwave frequencies propagate efficiently through Earth's atmosphere under most weather conditions, and the beam can be precisely directed to specific receiving locations. Unlike Tesla's proposed standing wave approach, microwave transmission doesn't rely on uncertain ground conductivity or variable ionospheric conditions. However, microwave power transmission faces significant challenges when scaled to global applications. The inverse square law still governs beam spreading, requiring enormous transmitting antennas to maintain focused beams across planetary distances. A microwave power satellite would need transmitting antennas several kilometers in diameter to deliver meaningful power levels to Earth-based receivers. Safety considerations present another major concern for high-power microwave transmission. The power densities required for efficient energy transfer could pose biological hazards to humans, wildlife and aircraft passing through the transmission beam. Regulatory frameworks would need to address these safety concerns while enabling practical wireless power deployment. Atmospheric absorption affects microwave propagation, particularly during precipitation events. Rain, snow, and fog absorb microwave energy at frequencies commonly used for power transmission, reducing system efficiency during adverse weather conditions. This weather dependency would limit the reliability of microwave-based wireless power systems. Tesla's vision of tapping into Earth's natural electrical systems has found modern expression in atmospheric electricity research. Scientists have investigated methods for extracting energy from the fair-weather electric field that exists between Earth's surface and the ionosphere. While this approach could theoretically provide continuous power without relying on sporadic lightning strikes, the power densities available through atmospheric electricity extraction remain extremely low. Advanced concepts in wireless power transmission include laser power beaming, which uses highly focused laser light to transmit energy across space. While laser systems can achieve extremely high power densities and precise beam control, they face significant challenges from atmospheric scattering and absorption. Clouds, dust, and atmospheric turbulence can severely degrade laser power transmission efficiency. The fundamental limitation affecting all wireless power transmission methods remains the conservation of energy principle. Energy cannot be created or destroyed, only converted from one form to another. Any wireless power system must account for conversion losses at both the transmitting and receiving ends, propagation losses through the transmission medium, and practical limitations imposed by antenna sizes and beam spreading effects. The harsh reality of Tesla's global wireless power transmission dream confronts fundamental physical limitations that no amount of technological advancement can overcome. The laws of thermodynamics, electromagnetic theory, and energy conservation impose absolute constraints on wireless power systems that render planetary-scale electrical distribution through Tesla's proposed methods scientifically impossible. Yet understanding these limitations illuminates the boundaries of what future technologies might achieve. The primary obstacle lies in electromagnetic wave propagation through Earth's natural systems. When electromagnetic energy enters the Earth ionosphere waveguide, it encounters resistance from both the planet's surface and the ionospheric layers above. This resistance converts electromagnetic energy into heat, creating unavoidable losses that increase exponentially with distance. Mathematical analysis demonstrates that power levels sufficient for global distribution would require transmitters consuming more energy than they could possibly deliver to distant locations. Tesla's concept of terrestrial stationary waves assumes that electromagnetic energy could propagate around Earth without the typical inverse square law losses associated with radiating systems. However, the Earth ionosphere cavity cannot support lossless standing waves due to the finite conductivity of both the ground and ionospheric plasma. Even under ideal conditions, electromagnetic waves propagating through this natural waveguide experience attenuation rates that would reduce transmitted power to negligible levels across continental distances. The variable nature of Earth's electrical environment presents additional insurmountable challenges. Ionospheric conditions fluctuate dramatically due to solar activity, seasonal changes, and diurnal cycles. Ground conductivity varies by orders of magnitude depending on geological composition, soil moisture, and geographic location. These variations would cause transmitted power levels to fluctuate unpredictably, making reliable energy distribution impossible through Tesla's proposed method. Modern atmospheric electricity research has revealed the limited energy available through natural electrical processes. While Earth's fair-weather electric field represents a continuous energy source, extracting meaningful power from this field would require collector systems covering thousands of square kilometers. The power density available through atmospheric electricity extraction measures only a few microwatts per square meter, insufficient for practical applications despite the enormous collector areas required. Lightning energy harvesting faces equally daunting obstacles. The sporadic, unpredictable nature of lightning strikes makes them unsuitable as a reliable power source. Even if efficient capture and storage technologies could be developed, the geographic distribution of lightning activity doesn't align with energy demand patterns. Tropical regions that experience the highest lightning frequencies often lack the infrastructure necessary to distribute captured energy to major population centers. However, emerging technologies suggest that selective wireless power distribution might become feasible for specific applications. Satellite-based solar power systems represent the most promising approach for large-scale wireless energy transmission. These systems would collect solar energy in space using photovoltaic arrays, then transmit power to Earth using focused microwave beams directed at ground-based receiving stations. The physics of space-based power transmission avoid many of the limitations that plague terrestrial wireless power systems. Solar energy collection in space operates continuously without atmospheric interference, clouds, or day-night cycles. Microwave transmission through the vacuum of space experiences minimal energy losses, and the beams can be precisely controlled using advanced phased array antennas. Several nations and private companies are actively developing space-based solar power technologies. China has announced plans to deploy a commercial space-based power system by 2030, while Japan continues advancing microwave power transmission research through JAXA. These projects envision orbital power stations generating gigawatts of electricity and transmitting it to Earth through microwave beams. Terrestrial applications of wireless power transmission continue advancing through technologies like dynamic wireless charging for electric vehicles. These systems embed transmission coils beneath roadway surfaces, allowing vehicles to receive power while driving. While these applications operate over distances measured in centimeters rather than continents, they demonstrate practical implementations of wireless power transfer for specific use cases. Quantum technologies might eventually enable new approaches to energy transmission that circumvent classical electromagnetic limitations. Quantum entanglement and quantum field theory suggest theoretical possibilities for energy transfer that don't rely on conventional electromagnetic propagation. However, these concepts remain highly speculative and face their own fundamental physical constraints. The legacy of Tesla's wireless power vision lies not in its practical implementation, but in its inspiration for continued research into electromagnetic phenomena and energy transmission technologies. His Colorado Springs experiments advanced understanding of high-frequency electrical systems and demonstrated principles that continue influencing modern wireless communication and power transmission research. Tesla's dream of illuminating Earth with lightning remains scientifically impossible, constrained by fundamental physical laws that govern electromagnetic energy propagation. Yet his vision continues inspiring researchers to push the boundaries of what's possible in wireless power transmission, seeking solutions that might one day deliver clean, abundant energy to every corner of our planet through methods Tesla could never have imagined.